Today we're on page 3 of the chapter 1314 Chem 1 packet, and we're going to talk about Dalton's law of partial pressures. In order to understand this, we're going to tell a quick story about a science extravaganza in the cafeteria, and we're going to have chemistry students, biology students, and physics students there. And as you know, the cafeteria has these cameras that are monitoring everything that goes on. And unbeknownst to everyone, these cameras have a special feature called the bumpometer. And the bumpometer records how many times students bump into the wall, because you're going to be walking around, there's food, there's music, there's chemistry demonstrations, and all kinds of science, fun activities. So people are walking around and bumping into the wall. So in the first hour, there are 1,000 bumps into the wall. 1,000 bumps. Now, as I said, there are 50 chemistry students, 30 biology students, and 20 physics students in the cafeteria. The question is, how many of these bumps are chemistry bumps? And you could figure out that it's half, because there are 100 students total in the cafeteria. So we are 50 out of 100. So 50 out of 100 times 1,000 equals 500 bumps. Let's do the same thing for the bio. They are 30 out of 100, and physics is 20 out of 100. So you could see that when you multiply these by the total, it's a fraction of the total. So this comes out to be 300, and this comes out to be 200. Now you could write the mole fraction as a decimal, of course, so this is going to be 0.50. And what happened was, back in the day before calculators took over the world, we used to use fractions instead of decimals more often. So that's why the term mole fraction is the way it started, but now we usually use a decimal, but fractions still sometimes make it easier. Okay, so you'll notice some interesting things. First of all, that the total mole fraction is always 1, because it's like 100%. And of course, you're going to notice that the total of all the pressures is 1,000, because that's how much there was total from the beginning. This is analogous to gases. So instead of students, okay, chemistry, biology, physics, now we have 3 different gases, okay? Gas C for chemistry, B for biology, and P for physics, okay? So 3 different gases are all moving around randomly in a container, and the gas that is present in the highest amount is the gas that's going to have the highest partial pressure. And then when you add up all the partials, you're going to get the total. And of course, all the mole fractions are going to add up to 1, which is like 100%. Now, let's suppose that all the physics students end up leaving. Their chemistry, or their physics teacher is a little tough. It gives them homework every single day. So they have to go home, watch some videos, do some homework. They got labs, all kinds of stuff. They got to go. So the physics students go away. Now we only have chemistry and biology students in the cafeteria. Well, you could think about it, that if all the physics students are gone, their collisions are no longer going to happen. So if these collisions no longer happen, the new total is not going to be 1,000. The new total is going to be now 800, because 200 are gone. So let's figure that out down below. The new total is going to be 800. 800. And now our fraction is going to be different as well, because we're no longer 50 out of 100, we're just 50 out of 80. And biology is also 30 out of 80. Now you could take the time to get the decimals for these, but I'd actually suggest you don't do that, because you're going to see something interesting here, that this fraction is like 5/8. 5/8 of 800 is going to be 500. And this is like 3/8, which is going to be 300. And so you see that the total is different than it was before, 800, which matches this, but the partials stay the same. So this is an interesting concept to know, that partial pressures do not change when you add or remove gas. So if we repeat the story, and we had some math students come in, they would add in their partial pressure, but it wouldn't change the partial pressure of anyone else. So partial pressures do not change when you add or remove gas. So this, now you could see the puzzle here that we have, and you could easily fill in a puzzle if you know some of it. So let's take a look at this diagram on the right. We see that we have 300 millimeters of mercury of this gas and 400 millimeters of mercury of that gas. That's a unit of pressure. So the total, of course, is 700. So the total pressure is 700, and the partials are given to you. So gas A is 300. You see gas A right here is, sorry, lost it, is this 300 and this is 400. So now you could work backwards because you know that the mole fraction times the total equals the partial. So if you simply divide, you're going to find that this is 3/7 and this is 4/7, which you could get the decimal if you want, which is 0.429 and 0.571. No matter how you slice it, you get 1 as the total. And of course, you're going to get 700 as a total for the pressure, which matches that. Okay, lastly, go to the bottom of the page. We're going to talk about air. Air is a mixture of gases. So move this up a little bit. And this little pie chart tells you all the gases that make up air. So we'll write down our partial pressures here. We see that the air is mostly nitrogen, 78.1%. So that actually is going to be our mole fraction. Oh, actually, I'm sorry. These are the partial pressures. I read that wrong. These are the partial pressures. So 78.1 in kilopascals. That's another unit of pressure. So 78.1 is that one. Oxygen is 20.9. And 0.97 is going to be the argon, which is, of course, very small, less than 1%. 1.28 for water vapor. And 0.05 for carbon dioxide. So the total is 101.3. That's 1 atmosphere of pressure. So 101.3 is the total. So again, we're going to work backwards, and we're going to find out the mole fractions. So when you divide the partial by the total, you're going to get 0.206 for the first one, 0.771, 0.00958. You should check these on your calculator to see how we got these. 0.0126, 0.000494. When you add this up together, you get 1. That's a lot of sig figs, I know, but we're just emphasizing that you get 1. It's like 100%. And of course, when you add up all the partial pressures, you're going to get 101.3, which matches the total. So 30-second recap. Mole fraction is how much of the gas you have out of the total. Mole fractions will always add up to 1. It's like a percent without moving the decimal. So this would be like, this gas is 20.6% of the amount, but you don't move it over. This is the total pressure, and all the partials add up to the total, and the one that has the highest partial is the one that has the highest mole fraction. One more hint, by the way. This has to be in moles, not grams. So if you look at the homework tonight on the worksheet, you have to work in mole fractions. So if they give you grams, you need to make sure you change it into moles and divide by the total moles to get the mole fraction, not grams.